All right, so let's get started. We're going to continue with graphical models again today. So let's go. Let's start with a review of what we were doing last time around. So we started by doing dynamic programming on graphs, meaning the variable elimination example. So we started with a very simple graph, which was basically trying to tell the probability of an event that was described by a SAT formula, a propositional logic formula. And we did some, we could have done it the hard way, right? We could have built out a table of the value of the formula for every possible assignment to the arguments and iterated over that whole big table. But since that whole big table is exponentially large, we wanted to avoid doing that, right? And so we did a form of dynamic programming. We took, we represented as a multiple sum of a product of some factors. And we moved the sums in as far as we could and did the partial sums, and that let us work with smaller tables, right? Everybody remember that? So any questions on that? All right. So that was the simplest example of a graphical model, right? It was the graph represented the structure of the formula, and the model was the probabilities of the coin flips that determined the individual arguments. There are a bunch of other graphical models, and we went through in some detail one of the most common graphical models, namely Bayes nets, right? So a Bayes net is given by a directed acyclic graph plus a bunch of conditional probability tables. So this was the canonical example, right? Our rusty robot, where the variable metal and the variable wet together influence whether the robot is rusty, right? And so there are a bunch of benefits to reasoning this way. The key ones are that you can represent your distribution using fewer parameters, right? If you represent it using a small set of conditional probability tables, you can have fewer than the exponentially many parameters it takes just to represent the full joint distribution over all of these variables. And fewer parameters means two things. It means better statistics. So if we are trying to, for example, learn all of these parameters, better to have fewer than more because, well, we need less data. And it also means faster inference, right? So instead of doing the whole exponentially big thing to figure out what the probability of some event is, we can do some work on the graph and get some answers much faster, right? So we showed that it was exponential only in the size of the largest table that we had to build, and we called the size of the largest table -1 the tree width of the graph. Okay. So that all sounds familiar? Good, because we're going to be doubling down on that sort of thing today. And the other cool thing about the graphical models was that some of your properties, like conditional independences, you could extract some without knowing anything about the conditional probability tables, just given the graph, right? And so you could do some reasoning about your distribution without having to worry about actual numbers, only the structure of the graph. All right. We did very briefly a couple of examples of conditional independence reasoning at the end of last period, but I wanted to go through those again because they were kind of fast. So blocking was the following sort of structure. We had one node, another node, and another node, right? And the structure looked like this. And if we observe this middle node, right, so without observing it, these two outside nodes are dependent. But once we observe it, that observation blocks the dependence between the two nodes, right? And the other sort of structure that was kind of interesting was what was called explaining away, right? So we had this sort of V structure where we have two parents of the same node. And these two parents are independent right now. But if I observe this, then explaining away couples the parents, right? So I observe this, let's say I observe that I'm wet. Well, if I, what was the, let's say I observe I'm not wet, right? Well, so for that to be true, either it could be not raining, or it could be that I'm inside, right, if I'm not wet. And so if I know that I'm inside, well, then I don't have to worry about, then I don't have to use that it's raining, that it's not raining as an explanation for me being dry, right? So there are these two possible explanations for me being dry, either that I'm, either that it's not raining or that I'm inside. And knowing one of the explanations to be true means we don't have to then invoke the other explanation. So there's a dependence between the two explanations conditioned on me being dry. Okay? So there's, these are examples of a general test called deseparation, stands for dependence separation in a directed graph. And the criterion is as follows. Two nodes are independent when there are no active paths between them. And the active paths depend on what our conditioning set is. Right? So for some conditioning sets, different paths might be active. And so we looked at the active paths of length 3, right? There were 5 of them. We had, right, if something like this, right, the other direction, we had a common cause, right? And then we had the V structure like that with a shaded node, right? And then the last one was we had this, son of D structure, right? So we had some long path here to an observed node, right? And those were the 5 length 3 paths. And then I was just going through, as the bell rang, so to speak, I was just going through how to deal with longer paths. So a node is active with respect to a particular path if one of two things happens, right? Either the node is itself shaded, or the node has some descendant that's shaded, and the arrows are like that, right? Or it's unshaded, and the arrows are like that, or like that, right? So these are the structures that we saw on the previous slide. And it's active if one of these, with respect to a path, right? So the path is coming through on these edges. There might be other edges entering or leaving the nodes, but the ones that matter are the ones on the path, right? And then it's inactive with respect to that path if none of these situations happen, right? And then an undirected path, a full undirected path, is active if every single one of the intermediate nodes is active with respect to that path, right? And then, as we said, if you can find an active path between two nodes, then they're dependent. If there's no active path, they're independent. All right? So that's a somewhat complicated definition, but does it make sense? So, for example, just looking at this graph, right, metal and outside, are they independent or dependent? How many people think independent? And how many people think dependent? All right. How many people never vote? Okay. Good answer. So that's right. They are independent. If I then shade Rusty, if I observe Rusty, right, they are independent or dependent. Good. Everybody, basically everybody got dependent. And they're dependent because of why? What's the active path between them? Somebody want to take a shot at the active path? I mean, I see people doing this sort of thing. So let's assume that that means you have the right answer, right? It's this path, outside wet, rusty metal, right? Wet is active because the arrows are going through it in the forward direction, They could also have been going through it in the backward direction, right? Rusty is active because it's part of a V structure and it's shaded, it's observed, right? Because I said conditioned on Rusty. And so both of the nodes are active, and so we're good, right? Yeah?
Is there any difference when you say observed? Like, is that the same as condition on?
Right. Observing and conditioning are synonyms in this context. So is shaded in this context because of the graphical interpretation. Yeah. Right. So the point is, I could ask for a directed path, meaning a path that respects the direction of the arrows, but I have to, in fact, deal with undirected paths, meaning paths that don't necessarily respect the direction of arrows, like this one, right? So here I'm following 2 arrows forward and 1 backward, so that's not a directed path, but it is an undirected path. More questions? All right. Yeah.
So, but like, we have data on all of these, presumably.
Right. So this is there's 2 situations, right? So you could think about learning the parameters of this network from data, or you could suppose that somebody else learned it and gave you the network and didn't tell you the data. So right now I'm in that second situation. Okay, cool. Now what if I add another node, let's say, we're metal and outside, and if we're metal and outside, we might be sparkly, right? Because the sun is shining off of us, right? So now, if nothing is shaded, metal and outside are still independent. If I observe sparkly, are metal and outside independent or dependent? How many people think independent? And how many people think dependent? Good job. All right. Everybody's raising their hands on the right thing. So despite the fact that there's an inactive path, right? Rusty is not observed, so this path is inactive. There is an active path between metal and outside, and so they're dependent, right? So it's, yeah.
In the second case, rains and wet are no longer dependent on metal, though.
Right. So if we condition on Rusty, rains and wet are dependent on metal. If we condition on Sparkly, rains and wet are not, because there's no active path, right? So you could make a path, right? This node would be active. This node would be active, but this node would not, because there's no descendant that's shaded. And so the path exists, but it's not active. That's a good point. All right. So for those of you who prefer algorithms, here's the algorithm, right? So the point of showing the algorithm is basically A, to make it more precise, and B, to point out that this is linear in the size of the graph to test the dependence, right? So what you do is for every observed node, you mark itself, and then you keep traversing parent links to mark all of its ancestors. Then you do a breadth-first search starting from one of your nodes, let's say X, and you traverse edges only if they can be part of an active path, right? And so that's actually a little bit tricky, right? Because activity depends on the last 2 edges you traversed. And so essentially the state of your search is the last 2 edges, right? The edge you previously traversed and the edge you're deciding whether to traverse right now. And then the same thing, we have to prune in order to avoid exponential time search, right? You could, visit every node multiple times. And you have to prune basically when you visit a node for the second time from the same direction, right? Because if you tested whether it was active when you came up from below, well, then if you come up from below again, the same test is going to be true. Okay? And then if you reach Y, you get dependence. If you don't reach Y, you get independence. All right? Cool. So the other thing that's maybe interesting is to talk about what's called the Markov blanket of a node, which sounds nice and warm and comforting. But what it is the minimal set of nodes that you have to observe to deseparate some particular node, let's say C, from everything else in the graph, right? And so, for example, if I don't observe anything, well, then C depends on some other stuff in the graph, A, B, and H, right? If I do observe, let's say, D, then it's going to depend on, N, M, and F as well, right? And so if I keep observing things, eventually what's going to happen is that I'll actually make it independent of everything, right? So the Markov blanket is defined to contain a node's parents, right? And so once I condition on the parents, every ancestor of the node is separated from that node, right? And then I can condition on the dependents, right? Descendants, and then everything that's below the node through one of those descendants becomes separated. But then I've tied F and G to C. And so if I condition on F and G, then finally I'm independent of everything else in the graph, right? And so it's the parents, the immediate children, and what are called the co-parents, nodes who share a child with C, right? So I'll just write that. Parents, children, and co-parents, right? And so it's useful to know this, right? That you can condition on a certain set of nodes and break off C from the rest of the graph, right? Because then once you know that the Markov blanket is in the conditioning set, you don't have to worry about anything else. Okay, so another example of a cool graphical test that you can use to tell something interesting about the distribution. All right, questions about Markov blanket?
I'm curious about how you're using independent, because if, according to what we just said, if D is shaded, then C is now dependent on N.
No, because so C would be dependent on F, but we shaded F, and so we blocked this path, right? So MFD, right? This node F, this path is not active because of blocking. Right? So that's a good point. By D, when we shaded and conditioned on D, we did make N, M, and F all dependent with C, but then we blocked everything above that by conditioning on the last node in that path. Right? So all of these questions point out something that's actually pretty important, which is that it's a little bit tricky, right, to apply these tests. And so you can memorize them, but unless you memorize and also practice with them, you're probably not going to remember in a week or two, right? So there are these graphical tests. They're not that complicated, but they're sufficiently complicated that if you don't practice with them, you will forget them. All right. So now let's get to learning, right? Or at least the first sense of learning, which is suppose that we have a fully observed Bayes net, right? Then it turns out that it's actually incredibly simple to learn it, right? So here's our, so fully observed means in every observation, I have a value for all of the variables. So I get a data set of a bunch of robots, and for each robot, I measure whether it's rusty, wet, outside, rains, right, all of these things. And then, so for example, I can compute what is the probability of metal. Well, there are 5 cases of which 3 are metal, so we'll just say 3/5, right? And that turns out to be the maximum likelihood estimate of that probability. Okay. Similarly for rains, right? That's 2 of 5, and outside is 4 of 5. Maybe we're working in the Field Robotics Center, so most of our robots are outside. And then here, right? Probability of wet given rains and outside. Well, I have to learn a bunch of numbers here, right? So I'll make a table, right, for different values of rains and outside. Could be both false, could be false, true. Didn't leave myself enough space. True, false, true, true, right? And so I'll go through and take particular values of rains and outside, right? So here, rains and outside are these 2 columns. So let's take false, true, right? Well, there are 2 places, here and here, where their false, true happens. In them, one is false, the other is true, right? So I'm just going to fill in a half in this in this point, right, in this box of the table. And so in general, this is going to be a table with one entry for every possible value of the parents, and then I'll fill in the probability based on looking at all of my data that matches and counting what the fraction is, right? And you've probably noticed a problem already, which is, let's see, so let's look for true false, right? So there are no cases of true and false, right, in this, and so I fill in 0 over 0, right? And so something's wrong, right? And you probably have guessed what the answer is, right? You remember from way back at the beginning of the course? I hear people whispering smoothing, right? The answer is Laplace smoothing. So you can use Laplace smoothing here. It's a good thing to do, right? So we'll just use, Laplace smoothing to fix that, right? And you can go through and fill in all of the rest of these things with whatever degree of Laplace smoothing you decide is good, right? And then the same thing for that table, okay? And so, yeah.
So in the top graph, we're only looking at elements that are true, but in the conditional probabilities we're not.
Right. So what you do is you two steps. You take your data and you restrict your data to look at only the places where the particular conditioning holds, right? So in metal, there's no conditioning, therefore there's no, it has no parents, so we don't have to condition on anything, and so there's no restriction of the data. And then, in that restricted set, you count how many are true, right? So here, the restricted set is the whole thing, right? And so 2 out of those 5 metal is true. Here, the restricted set, right, was just, right, false, true, right? These are the only ones that match false, true. And so out of those, there's a false and a true, and 1 out of 2 of them is true, right? So there's 2 steps. You restrict your data to match the conditioning, and then you estimate the probability from that remaining data. I saw another hand over this way. Yeah.
Other than true, false, we have all the variables.
That's right.
So we can sum it over and stick it in the.
That's right. So we don't have to use Laplace smoothing, although it's still a good idea, right? You should use Laplace smoothing either everywhere or nowhere. So so let's say we're using it everywhere, right? And we can then fill in everything. If we use it nowhere, then we can fill in 3 out of the 4 entries of the table. The other one will be 0 over 0. Okay. Yeah.
In this case, shouldn't it be 0, since if you're not outside, you don't get wet?
So you are using a prior. If you're not outside, you don't get wet, right? So you can, instead of learning it from data, you can go through and say, oh, I have an idea about this domain. I'm going to fill in the conditional probabilities based on my own knowledge. And that's actually a great way to get a Bayes net. It was probably invented before learning Bayes nets was invented. And you can use any combination, right? You can make a prior based on your knowledge and then augment the prior with some actual data and any combination of that.
Well, but even with what you've got, doesn't the fact that true, false doesn't show up in the table mean it's not the condition you care about or possible?
Well, so if we had a lot of data and it never showed up, I would believe that we probably don't care so much about it. But with only 5 cases, there's a decent chance that we missed something, right? And especially if we have a large parent set, if we have 5 parents, there's 32 possibilities. If some of the possibilities aren't all that probable, we could easily miss them unless we have a pretty large data set, right? And so it doesn't mean, and also we should distinguish between the conditioning being impossible, right? If it's truly impossible, we don't need to worry about it, and the child variable, right? So if the conditioning is just unlikely, we don't know anything about what the child variable is going to do in that conditioning situation. Yeah?
How could we do random smoothing here, because my observations are just binary. My observations are just binary, true and false.
That's right. So Laplace smoothing in this case, right? Here I have 0 trues and 0 false, right? So I would instead say 0 trues, 0 plus lambda fake trues that I get from Laplace smoothing, right, over number of trues, which is 0 plus lambda, plus the number of falses, which is 0 plus the lambda fake falses that we have, right? And so I would get a half in this situation, right? And lambda here is the degree of Laplace smoothing, right? So let's do another one with Laplace smoothing, right? So the false here, right, that's this row. There's, this one, wet, is false, right? So without Laplace smoothing, I would estimate 0. With Laplace smoothing, I would estimate 0 plus lambda over 0 plus lambda plus 1 plus lambda, right? Which is lambda over 1 plus 2 lambda, right? Which is close to 0, but not exactly 0, depending on exactly what you make lambda be, right? All right, so that's learning fully observed Bayes nets. So you now know enough to be dangerous. You can go learn a Bayes net from data, and you can use variable elimination, which I showed you last time around, to make some inferences based on that Bayes net. All right, so that's good. So what next? Well, you might ask, what if you have some variables that are only sometimes observed or never observed, right? And in both cases, there exists an algorithm for learning it, but it's a little bit more complicated. We may get to it in a number of lectures. So basically, the simplest conceptual algorithm is what's called expectation maximization. And in this case, it works out to alternating two steps. The expectation step, which is anything that you haven't observed, you do inference in your Bayes net, you fill it in with its conditional expectation in every case given what you know from the Bayes net, right? And then maximization, you pretend that the expected values are in fact exactly right, that you observed if the expected value was 0.7, you observed 0.7 trues and 0.3 falses in that situation, right? So that's the algorithm. It's pretty simple to implement, but there are also a ton of toolboxes out there that you can use. And we'll maybe do some more detail on it later. All right? All right, so that's Bayes nets. Maybe the most common type of graphical model that isn't a Bayes net is what's called a factor graph. And so instead of a directed graph, the graphical part of a factor graph is an undirected bipartite graph. Instead of the conditional probability tables, there are these things called factors or potentials that are the numerical part of the factor graph. And like a Bayes net, we can use it to represent any distribution, and we can infer conditional independences from the graph structure. But some distributions are better represented as Bayes nets, and some are better represented as factor graphs. And basically, the difference, what I mean by better represented, is that the representation is more faithful, meaning that either the number of parameters is smaller or the fraction of conditional independences that you can recover just from the graph is larger, right? So two, in general, incomparable representations. Both of them have actually fairly similar algorithms to work with them. Okay? So let's go into factor graphs. So here's the Rusty Robot factor graph, right? So the bipartite graph I've drawn with two types of nodes, squares and ovals, right? So the squares stand for factors. The ovals stand for, well, variables that I'm observing in the distribution. And I've taken a factor and I've connected it to every variable that participates in the factor, right? And so this same factorization that I made before, it's also represented by this graph, right? So here, probability of Rusty given metal and wet is considered to be a factor which connects Rusty, metal, and wet. Okay? Does that make sense? All right, good. So there are a few different conventions that you might see, right? So here's what I drew on the last slide. You can also omit the unary factors, right? So that lets you, it's kind of like the chemistry convention of omitting hydrogen atoms from your organic molecules. Basically, assume that they could be there. You can fill them in. They don't affect the algorithms much, right? So that would look like this. And then the other thing that people often do is instead of a factor, they'll make a clique. That connects all of the nodes that the factor would connect to. And if you do that, it's called a Markov random field, right? But every Markov random field is equivalent to some factor graph. Yeah?
Factor graph, could you just say that the ovals label the edges?
What's that?
Could you just say that the ovals are labeling the edges?
Well, you could have, it doesn't happen here, but you could have more than two. You could have 3 or more factors connected to a single variable, and you can have 3 or more variables connected to a single factor. So it really is a bipartite graph, right? But what people do sometimes do is if you have just a binary factor, they'll omit the factor node and just make it an edge, right? And that's a special case of this representation, right? So here, if you just had a binary factor, it would be a 2 clique, which is an edge, right? And so I should point out, by the way, that Markov random fields lose a little bit of information compared to factor graphs because, for example, here in metal, rusty, and wet, I can't tell whether I have 1 factor that connects all 3 of them or 3 binary factors that connect them, right? And people consider that to be a distinction that's sometimes OK to lose because the dynamic programming algorithm is going to be very similar. Yeah? Right, so you can go from a Markov random field to a factor graph, but if you go from a factor graph to a Markov random field and back to a factor graph, it might not be the same factor graph, right? It might have lost some information in the process. So all of these representations, right, a factor graph, a Markov random field, and a Bayes net, you can interconvert between any of them, but you might lose some information when you make the conversion. And so if you convert in a circle, you might not get back to exactly where you started, but you'll get back to something that can still represent the same distribution. It just might have lost some conditional independence relationships. Okay? All right. So when you convert a Bayes net to a factor graph, right, all of the factors wind up being conditional probability tables. But that's not necessary. You can have a general factor graph where the factors are just any tables which have as arguments all of the variables that the factor is connected to and have non-negative numbers as every entry of the table, right? So the intuitive meaning is basically that a higher number means that that combination of assignments is more likely, and a lower number means less likely. So in a conditional probability table, that's clearly true. But like I said, it doesn't have to be a conditional probability table. It doesn't have to sum to 1 for all values of the parent variables. Okay. So what is the distribution in that case, right? So in general, the distribution is going to be the product over all factors I of, I'll write phi I for the ith factor, and then I'll write x sub I, right, for the arguments of the ith factor, right? And so x sub I could be something like A, C, and D, right? If you have a factor like this connected to A, C, and D, right? And then we're going to divide the whole thing by a normalizing constant, right? And what that normalizing constant is going to be, well, unsurprisingly, it's what you need to make the whole thing sum to 1, right? So it'll be sum over all assignments to all of our variables x, right? So x is, right, this is shorthand for sum over A, sum over B, sum over C, and so forth. Sum over all variables of the thing that we want to make sum to 1, product over I, phi I of xi, right? And actually, let's just write, I'll write a little bit, I'll write this, right? To say that this is not just the ith element of x, but this is something special, right? It's the neighbors of the ith factor. Okay? So, so that's now a complete definition of a factor graph, right? You have an undirected bipartite graph. That's the graphical structure. You have the factors, which are tables, one for each factor, that say how likely the assignments to that factor's neighbors are, right? And then you multiply them all together and normalize to get a probability distribution. Make sense? All right. So just like in Bayes nets, there's a graphical test for independence and for conditional independence. The test is simpler though. You just cover up all nodes that are observed and then look for an ordinary undirected path in the remaining network, right? So if we take a look here, right, according to this factor graph, are metal and outside dependent? Well, yes, because we go through, right, that path and connect them. Okay? So something weird just happened, right? We showed before that they were independent, and now we showed before that they were dependent, right? And it's the same distribution, so how can they be both independent and not? Anybody got an answer? Yeah. That's right, it's no more a directed graph. Mm-hmm. Right. So you're saying we lost information in the translation to a factor graph. Right. And that's exactly right. We lost some information, so now they are independent, but we can't determine that just from the graph structure alone, right? It's an accidental independence at this point. And so that'll actually, this is this is what happens, right? When you do the conversion, the graph structure winds up not containing all of the information, but of course, since it's the same probability distribution, the same set of conditional independences have to hold. It's just that some of them are now accidental instead of inferable from the graph structure. Yeah. It might be that you've developed some fancy, the question is, why would we want to use one of these graph structures that loses information? And the answer is, it might be that you've developed some fancy new algorithm that only works on Markov random fields. And so you want to take your Bayes net and turn it into an MRF so you can run your fancy new algorithm on it. All right. Okay, so, right, I said this, but I'll just write it. Right, we have an accidental independence. All right, so we can do now exactly the same sort of dynamic programming for inference as before, and I've gone ahead and written everything out so that we can go through this one a little bit faster because you've already seen one, but I wanted to show you what it looks like on a factor graph instead, right? So here we have, right, the joint probability is the product of all of these potentials divided by a normalizing constant. And I've written out these potentials. If I remember right, when I made these potentials, it was the same as the previous. Yeah, it looks like it's the same. They're just the conditional probability tables, but I've written them now as potentials. And the typical sort of question we might want to answer is conditioning on rainy being false and rusty being true, what's the probability that we're wet, right? And so what are we going to do, right? So first step, we're going to incorporate evidence. So that means we condition on rainy being false and rusty being true, right? So let's see. We go through all of our potentials and see which ones have rains or rusty as an argument. This one has rains, right? And we're conditioning on it being false, and so we just cross out the true, right? We don't need to deal with that anymore. Let's see, rains we know is false, so we'll cross out everywhere where the first argument is true. Yep. And here, rusty is true, that's the last argument, so we'll cross out all of the elements of the table, right, where that's not true, right? And now Rusty isn't an argument here, Rains isn't an argument here, Rains isn't an argument here, and actually this potential has no arguments left, right? So that's kind of interesting. So what I'm going to do is I'm just going to get rid of the potential as a whole, right? And what that means is that this 0.3 is just going to get collected into the normalizing constant, right? It's the same for every remaining assignment, and so, right, that's what we want. And so now I'm going to calculate the probability of, right, of metal outside and wet given Rains equals false and Rusty equals true, right? And phi 2 is totally gone, and then phi 4 and phi 5 have lost arguments, right? And then I'm going to calculate, this is now a different normalizing constant, but I still need to calculate the normalizing constant so that this probability sums to 1. Okay? So hopefully I've copied that correctly onto the next slide. Looks like the same thing. So the remaining nodes are metal outside and wet, right? And the query is the probability of wet, you know, given stuff, right? And so outside and metal are nuisance variables. We're going to have to marginalize them away, right? And the marginal is the sum over all possible values of outside, sum over all possible values of metal of this thing here, right? Phi 1 of M, phi 3 of O, phi 4 of O and W, phi 5 of M and W, right? Divided by the normalizing constant. Okay? And so that's hopefully what I copied to the top of this slide. And so now what we're going to do is we sum out the nuisance variables in turn. We can again do it in any order. Some elimination orders are easier than others. So if we do outside first, right, we move the O sum in as far as possible. We catch phi 3 and phi 4 both have O as an argument. And so we make a joint table between phi 3 and phi 4. So I've copied phi 3 and phi 4 right here. And we make a new table, which I'll call phi 6, right? So these things go to there, right? And I'm going, right, so phi 6 is going to have just W as an argument. And the way I do it is I multiply, right? I extend phi 3 so that its arguments are both O and W. Then I pairwise multiply, and I sum out O to get this, right? And then the same thing, right? So after I do that, I'll have phi 6, and then I'll still have phi 1 and phi 5 left, right? So I want to multiply all of those things together and get phi 7, which is this, right? And I've done the arithmetic ahead of time. And then finally, phi 7 is the only thing left. It depends only on W. So I normalize it over W, which is easy because there's only true and false to consider. And so that's 8 over 17, it turns out. All right? So is that clear? You guys could all do it on, say, a homework? Yes? OK, cool. So there are advantages both to directed graphs and to undirected graphs, right? First, they represent different sets of conditional independences. Second, well, the algorithms look slightly different for directed and undirected graphs, right? So for directed graphs, there are some things that I can do with no computation. If I condition only on the ancestors of a node, right? If I condition on all of its ancestors, I can then, or you know, some cut, right, across the ancestor graph, then I don't actually have to do much in the way of calculation to get the conditional probability distribution of the node, right? Whereas no matter what, in an undirected graph, I have to compute that annoying normalizing constant in order to get any information whatsoever, right? Yeah? No, phi 6 and phi 6 happens too because it was doing a conditional probability of child given parents, but phi 7 does not, right? So you see that phi 7 sums up to whatever 0.072 plus 0.081 is, right? 0.152, right? So our intermediate quantities don't have to sum to 1. And in general, it's almost an accident when they do. Here, because we got our factor graph from a Bayes net, there are going to be some that actually do sum to 1 because they actually represent valid conditional distributions. But in general, the factors are not, they don't represent conditional distributions at all. All right. More questions about inference? All right. So normalization, right? So we have to do normalization before we can do just about any interesting computation, or as a part of just about any interesting computation. The way we do normalization is through variable elimination. At least that's the only way I've showed you so far. Every time we do an elimination, what it does is it introduces a new table, right, which has as arguments all of the current neighbors of the eliminated variable. And then it makes some old tables irrelevant, right? You just throw them away. And that's what I mean by current neighbors, right? So if you had a neighbor in an old table, it doesn't matter, right? So the structure of the graph essentially changes as we do the eliminations. Okay. And every elimination order potentially introduces different tables. Some tables are going to be bigger than others, which means that you might take more or less computation to get the answer you want, depending on your elimination order, and also on which of the many different graphical model structures that are correct descriptions of your distribution you happen to use. All right? Make sense? So the thing that determined, the biggest determiner of how expensive it was going to be was the tree width. I defined it, but I wanted to give you a few examples, right? So if you have a chain, right, so these are all going to be factor graphs, but essentially the same thing is going to be true for directed graphs as well. So if you have a chain, what's the biggest table that you ever have to do? One variable, two variables, three variables? People are unwilling to commit, right? So let's think about it, right? So what would be a decent elimination order for the chain? What would be the first variable that I would want to eliminate? What's that? One of the ends of the chain, yeah, that's right. So let's say I eliminate this variable, right? So it currently participates in a table between two variables, it and its neighbor, right? So when I eliminate it, that's the only table that this variable participates in, right? So when I eliminate it, what happens? Right, a table with two arguments, I take away one argument, 2 minus 1 is, all right, 1, good. So I have a table with one argument left, right? And I multiply that table into this bigger table, right? So I can multiply it into anything that shares an argument with it. So let's multiply it into this table. And now I have a chain that's one shorter, right? So the power of recursion, I can just keep eliminating an end. I build a table of size 2 variables, right? Every time I do that. So the biggest table I build is size 2, that's right. And so the tree width is 1 less than that, which is 1, right? Right? So the biggest table, this would be an example of the biggest table I built, right? How about a tree? Somebody wants to say 3 for the size of the biggest table. So what would be the elimination strategy? From the end again, right? So any leaf of the tree I can eliminate, right? So let's say I eliminate this leaf. I have a table of size 2, right? I sum out one of the arguments. That gives me a table of size 1. I multiply it into either one of these two tables, right? And now I have a tree again. And so again, the tree has tree width 1. That's why you subtract the 1, is so that trees have tree width 1. And so in general, you can just repeatedly eliminate a leaf. Every time you eliminate a leaf, you wind up, dealing with a table of size 2. Yeah.
You say either one. Is there like a specific algorithm to choose which one, or you do both?
No, you don't do both, right? You have to do it into one or the other, right? Or just leave it around until you need to eliminate this variable, right? But the point is you have to multiply it in exactly once. And there is no benefit that I know of to doing it one way or the other unless maybe one of these potentials is sparse, right? Then you could multiply it into the sparse one and save yourself some computation. Right? So chains and trees have tree width 1. Once you know trees have tree width 1, well, chains are trees, so they have tree width 1. Parallel chains. So what would be a good elimination order for this, right? So imagine that it's 3 chains high and it extends arbitrarily far off into the distance. Yeah, that's right. So pick a corner and then what? Right, so if I were to eliminate this corner, right, I would get rid of these 2 potentials and then introduce a potential here, right, between these 2 guys, right? So what should I do next? That's right. Yep. And so in general, what I'm going to do is I'm going to eliminate everything in the first column before eliminating anything else, right? And the last node that I eliminate in the first column, it's going to be connected with a potential to every single one of the nodes in the next column, right? And so I'll have 3 plus 1 is 4, right? Minus 1, so the tree width is going to be 3, or number of chains. Right? So after I eliminate all but one of these things, I have this guy, let's say, connected to this, this, and this. It's a click of size 4. Then I eliminate it, and I'm back to another smaller set of parallel chains. And so by recursion, I never have to, by induction, I never have to do more than size number of chains plus 1. Okay. How about a cycle, right? So which node should I eliminate first? Yeah, everybody's laughing. It makes absolutely no difference. It's completely symmetric. So let's eliminate this guy, right? And what I'll do is connect these guys, right? And so I'll temporarily have to build a table with 3 arguments, but then I'll eliminate one of them, get to a table with 2 arguments, right? And so the tree width will be 2, right? And I've gotten back to a cycle, a smaller cycle, and so it eventually finishes. Right? So, so that's tree width. So why is tree width important, right? It tells you how expensive inference is going to be. And in particular, since inference is exponential in the tree width, it's pretty important to keep the tree widths of your models as small as possible if you want to do exact inference. Right? We can handle, tables of size, let's say tens of millions. If it starts to get to billions, then we're somewhat in trouble. Okay, and we'd have to resort to some kind of approximate inference. Okay, so we've been talking a lot about inference. The definition of inference, I can give you the definition now that I've used the word for 2 lectures, right? The definition is to take some prior and some evidence and compute the posterior or maybe some marginals of the posterior, right? And for graphical models, the prior is represented as a graphical model. The evidence is some observations of, let's say that one of the variables is true, and then you want to do variable elimination or maybe some other algorithm to do inference and get the posterior or some marginals of the posterior. And there's a famous general algorithm for doing this that's called message passing or belief propagation. And we're going to go through it. So it has the following steps. We build a data structure called a junction tree. We instantiate our evidence into that junction tree. We do message passing. That's how it gets the name, how the algorithm gets the name message passing. that lets us read off the answer, except that there might be some nuisance variables the way we saw in the previous example, and so we have to sum out those nuisance variables, right? And that's the whole thing. And belief propagation sometimes refers just to that part, right? But these other two steps, building a junction tree and eliminating the nuisance variables at the end, they're pretty important too, and so people often assume that they're part of any problem where you're applying BP. Okay. And so the point is that you can, the point of the junction tree is that you can share the work of building it among multiple queries, right? So we could instantiate different types of evidence, maybe even on different nodes, and do multiple queries on the same junction tree. But different junction trees are going to be better for different queries, and so we might want to build several and keep them all around, right? Or have a least recency, have a cache, right, and keep the 10 most recently used ones. Okay, so belief propagation is going to be better than variable elimination for a couple of reasons. One, it sort of organizes the computations of variable elimination in a nice way. But two, it actually gives you more information than variable elimination. So for example, suppose we wanted all one variable marginals of the posterior. We could do n runs of variable elimination to get those n one variable marginals. Or you could do belief propagation, and it'll be the cost of essentially 2 runs of variable elimination, and it'll get you all n of those marginals. And in fact, every other marginal on some table that you would have built during any of those variable elimination runs. Okay? It's a complicated algorithm, so I wanted to give you a couple of readings to take a look at. One of them is this paper by Shishang et al. Called Factor Graphs and the Sum Product Algorithm, with the link that's on the slide. And the other is Daphne Culler's book, which we emailed some readings around to you guys. Okay. And because it's complicated, the main things that you need to understand, I figured I'd tell you ahead of time. One is, based on the algorithm, how expensive is inference going to be, meaning what tables are going to get built and how big are they? And second, what does a message represent and why is it something that we care about, right? And so to get you the answers to those questions, we're going to dive into the details of the algorithm, but those are the main things that you should be taking away. All right? Okay, so a junction tree, otherwise known as a clique tree or a join tree, it represents the tables that we build during a variable elimination run. And so every elimination order is going to help us build one junction tree. But it turns out that it actually will help us build several different junction trees, potentially. And also, for each junction tree, there are many different elimination orders that you can run using that junction tree, right? So there's a many-to-many correspondence. A junction tree is defined as a tree, hence the name, whose nodes are sets of variables, which are called cliques, and they correspond to the same thing that the cliques were in Markov random fields. And the junction tree has to contain at least a clique for each one of our factors. So what does that mean, right? It contains a clique for a factor if the factor's arguments are a subset of the clique, right? And then it also has to satisfy a property that we call the running intersection property, which sounds kind of arbitrary, so I'm not going to define it now. I'll define it later after the motivation becomes more obvious. All right? So an example of a junction tree would be something like this, right? So we have ABC is a node, right? That's a set of our variables. It's connected to another node with, let's say, ABD, right? And then, I don't know, let's connect this to ABE, and then also to, I don't know, BDF, right? So that's a junction tree, right? And it happens to satisfy the running intersection property, even though I haven't defined what that is. All right? So we're going to be working with this example network with elimination order C, E, A, B, D, and F. right? And so it has factors when we represent it as a factor graph for every click. CAB, ABE, ABD, and BDF. Okay? So here's the algorithm for building a junction tree from an elimination order, right? Basically, what the algorithm is we run variable elimination, and we look at the tables that we build, and the largest such tables become our nodes in the junction tree, right? So what does that look like? We start off by saying that our table arguments are the null set. We've visited no nodes. Then we go through nodes in our elimination order. We extend our table to contain all unvisited neighbors of the current node, right? So we look at the node xi, we look at the neighbors of that node, we throw away nodes that we have already visited. We take the previous set of table arguments and we add in the new neighbors, right? And so we're going to wind up building a table that has those as the arguments, right? Because we're going to multiply together all of the potentials that xi participates in. Okay? Then we're going to sum out xi, right? So I'm going to say si is ti minus xi. So we're going to sum out xi. And we're going to mark xi as visited. Okay? And we just do that throughout our full elimination order. Okay? And then we're going to build a junction tree from the values that s and t took on during this loop, right? So the nodes in the junction tree are going to be the local maxima of t, right? The t that are not contained in any other t. And the edges are going to be basically the local minima of S, right? So after we do a run of marginalizations without introducing any new variables, those are going to give us the edges. So let's go through to our example, and I'll show you what happens, right? So here's S, here's T, right? So at round 0, S is the null set, right? Then we visit C, right? So T becomes the null set plus all of the neighbors of C, which is A, B, and C, right? And then we eliminate C, so we get just A and B, right? So that's on, right? Then we visit E, right? So we add all of the neighbors of E to our set, right? Which is, well, A, B, and E, right? And then we eliminate E and we get A, B instead, right? Yeah.
You have already visited A and B.
So far I should write what the visited is, right? So here the visited is C, here the visited is C and E, right? So we haven't visited nodes until we eliminate them. Okay, it doesn't really matter because they're already in our neighbor set, so adding them again wouldn't matter, right? Okay, so now A, right? So A has A, E, B, and D as neighbors, right? But we've already visited E, so we just add B and D, right? So we now have A, B, and D, and then we eliminate A, and we get B, D, right? And so C, E, and A, right? And now we finally add B, D, and F, right? So we visit B. B is the first node that has F as a neighbor, right? And then so C, E, A, B, right? We eliminate B, we get D and F, right? And then it's just going to be DF. We eliminate D and get F, and then F, and we eliminate F and get the null set, and we're done, right? And so these are all of the tables that I've built, right? The maximal tables here, right, are this one, this one, this one, and this one, right? And so these are going to be the nodes of our junction tree. All right, so everybody okay with me with this so far? All right. So the edges, I want to talk a little bit about the edges. So I said before that there's going to be edges that depend on these values of S. So what's actually happening in the variable elimination algorithm, right? We had this table ABC, we marginalized out C, and we got a smaller table whose value was A and B, right? Whose arguments were A and B. This table, I'm going to call it a message, right? So basically, what that means is that from this large click, I summed out some variables, got a smaller message, which I send on to the rest of the algorithm, right? And so this is going to get multiplied in to some other table at some later point in the algorithm, right? Same thing here. I had ABE, I summed out E, and I made a smaller table, which is going to get multiplied in at some point later in the algorithm, right? So let's take a look here, right? The ABE, the place I have to multiply it in is to this table, right? There are no other later tables that have A and B as arguments both, right? So what that means is I'm going to put an edge between these two clicks, right? Now here, right, I could put an edge. I could multiply in AB into this table, right? Or I could just hold it around and multiply it into this table, right? It doesn't actually matter. As long as I multiply it in once and only once, I'm going to get the right answer, right? And so let's just, since I have the choice, we'll make an edge like that. And then, right, so BD, the only place I can multiply it in is there. And that's my junction tree, right? So, so to summarize, basically, what we do is we take the maximal values of t, those become the nodes of our junction tree, and then our messages, right, are after we do a run of variable eliminations, right? So if I had eliminated, let's say, you know, if this had been, you know, A, B, C, and Q, and I eliminated both C and Q, right? I wouldn't have to have a message until after the table reached its smallest point, right? So for every message, I can then put an edge in the tree, and the edge says, what other click am I going to multiply it into? What other table am I going to multiply it into later in the algorithm, right? And so it's always OK to connect things in a line from this variable elimination order, but it could be that I can delay multiplying in one of the messages and get something that's not a line. All right? So is everybody happy with that? So the junction tree is basically a record of the progress of our variable elimination algorithm, right? It tells us what are the tables we're going to have to do, and it tells us what are the things that we're going to have to multiply into some other table because we've marginalized out of an existing table. Okay. All right. So I think I said this on the previous slide, right? So I have a pattern of a local max, right? And then here's a local min, and then another local max, and so forth. And so each one of these things gets paired with its immediately following local minimum of the size of the table, right? And then this can get multiplied into the immediate next one or any subsequent one where Sj minus 1 is a subset of Tk, right? You can multiply it into any later table which has a superset of the required arguments. All right, so the running intersection property, I mentioned it before. Once a node is added to our table, T, right, it stays in both S and T until we eliminate it, and then it never appears again, right? So what does that mean? In the junction tree, that means that all of the nodes, all of the clicks, all of the sets containing X form a connected region of the tree, right? So if I look at a node containing X and I look at a node containing another node containing X, then there's going to be a path between those two nodes, and every node along that path will also be labeled with a set that contains X. Right? And if that's true for every variable, that's the running intersection property, right? So it seems kind of arbitrary until you look at it in the context of the algorithm, right? In the context of the algorithm, it makes perfect sense that it would be true. All right? So now we have a definition of a junction tree. We have an algorithm for building one, and we have some of its properties. All right. So let's see. You may have heard the phrase moralize and triangulate, kind of an arbitrary sounding phrase, but I wanted to point it out because it's another algorithm for building a junction tree, and it's maybe the more commonly known one, right? So moralize and triangulate basically what it does is it goes from the graphical part of a graphical model to a graph that we can use directly to build a junction tree, right? So let's take some arbitrary network, right? We'll make a directed graph. I don't know. And we'll say that like that, right? So here's a directed graph. So moralizing and triangulating. So first moralizing. So we'll take the same graph. We'll put in an undirected edge for every directed edge, right? Like that. And then we'll moralize. So what does moralize mean? It means marry the parents of the node. That's why it's called moralizing. Right? So D's parents are A and B. We put a line between A and B. F's parents are D, C, and E. So we put a line between every pair of parents of F, right? And then triangulate. So what does triangulate mean? It means that we want to make the, right? So moralize is marry parents. And triangulate is no chordless 4 cycles. So what does that mean? So let's see. We don't actually have an example of a 4 cycle in this. Well, we have a 4 cycles, right? So C, D, F, and E, right? And so that's a cycle among 4 nodes. We are also interested in cycles among 5, 6, and whatever. This cycle has a chord, right? So it has an edge going across it. It's not just a loop with no internal edges. And so it's a chorded 4 cycle. What chordless 4 cycles, basically we have to eliminate them all. And the way we do that is we find one, a cycle of length 4 or greater, that doesn't have a chord, and we just add a chord in, right? And what that chord corresponds to, it's saying something about what elimination orders we're considering using. Basically, what it's saying is that at some point, we're going to be eliminating a node of which both C and F are neighbors. And so we'll make a table that has both C and F as neighbors. OK? Right, so that's moralizing and then triangulating. And to build a junction tree, you just look for clicks in this graph. Right? And so the nodes of the junction tree are going to be exactly the maximal clicks in the graph, the ones where no superset is also a click. And we can put the edges in any way that maintains the running intersection property. And so you can see why I started with the other algorithm, right? This is a very arbitrary sounding algorithm, but it does happen to work. The proof of that is in the Kohler readings. You'll probably hear the phrase moralize and triangulate at some point reading some paper, and so now you know what it means. But I think the other way of thinking about it is sort of much easier to reason about. It's basically you do a run of variable elimination, and you see what tables you build, and you see where you multiply them in. All right. So I think that's everything, and this is a good stopping place. We'll see you again on Wednesday.